So here we will try to solve a partial differential equation using the Fourier transformation. Okay, so we have the following partial differential equation in red. Okay, with initial condition that u of x when y is 0 is equal to h of x, where h of x is an absolute integrable and continuous function. Okay. So we can recall the rules for how do you apply the Fourier transformation to the derivatives of a function. Okay, so if we take the Fourier transformation of the derivative to one variable of our function, it will just give us j omega times the Fourier transformation of that function. Okay, where j is of course the imaginary numbers. Okay, you can use I if you want. And so if you take the second derivative, it's just j omega squared times the Fourier transformation of your function. So it's equal to minus omega squared times the Fourier transformation of your function. And if you take the Fourier transformation with respect to another, with the derivative of another variable, okay, so here f of d dy, the derivative just comes out, okay. So basically the Fourier transformation ignores the derivative for also if you take the derivative with respect to another variable. Okay, so we can try to apply that to our function. Okay, so we'll get minus omega squared times u transformed plus the second derivative, plus the second derivative with respect to y times our u transformed, and that is equal to 0. Okay, so now we can rearrange our equation. So we will get that the second derivative with respect to y is equal to omega squared times our u transformed. Okay, and now we can state that u hat is equal to c1 hat times e to the minus absolute value of omega times y. Okay, why? Because basically we have this equation here which states that the second derivative of our function is equal to the function itself times u omega squared. Okay, and the only function that allows us to do that is the exponential function. Okay, if you derive it, you get the same function again, but just the exponent comes in front of the function. Okay, and we have minus absolute value of omega because we require y to be we require our function to be bounded if y goes toward infinity. Okay, if y goes toward infinity, we want that our function converges to 0. Okay, now we have our initial condition which states that u of x when y is equal to 0 is equal to h of x. Okay, and if you take the Fourier transform, it doesn't change, so we will get the u hat of x0 is equal to h hat of x. Okay, and so we will get that if we plug in y equals 0, e to the 0 is just 1. Okay, so we'll get the c1 hat is equal to h hat. Okay, now we can use the inverse Fourier transform to get that u, if you apply the inverse Fourier transform, we get u is equal to the inverse Fourier transform of c1 hat, which is h hat. Okay, times the inverse Fourier transform of e to the minus omega y. Okay, And so the inverse Fourier transform of h hat is just h. And now we can use the convolution theorem, which states that the inverse Fourier the product of two inverse Fourier transform is just equal to the convolution of these two functions. Okay, and so we'll get h convoluted with f inverse of e to the minus omega y. Okay, so just that you know it, the convolution of two function f and j is equal to the integral from minus infinity to infinity of f of tau times j of t minus tau d tau. Okay, but you can leave it in this form. It's okay, and so it will be our function. Okay, so just what you need to do is note these rules here for the derivatives. If you apply the Fourier transform to the derivative of a function, you can apply these rules, then solve algebraically, and then do your inverse Fourier transform, and so you can solve your differential equation. Okay, thanks for watching.